Okay, so let's continue with part B of the previous example over here on a clean slide. So kind of the word of the day for these videos is going to be linearization. So what I would like to do is take this sine equation okay, which is a very nonlinear curve in general, a nonlinear function, but locally we can linearize it. So this is true anywhere. So for example, if I were to zoom in at a really locally at a point on the graph, then it would look linear, right? And we're all witnesses to that because we live on a very curved surface, but we're zoomed in really close, so it seems flat to us. And the same happens for curves. So we can approximate functions at least locally with linear functions. And that's what's called the linearization of an equation, which is also like the tangent approximation. So here we are, and let's say we're interested in the behavior of this pendulum when theta is equal to 0, if theta is small. So if we were to zoom in on the graph over here, then we can find its formula by saying, let's find the derivative of this. So let me just call this function f of theta. Then we just want to make sure that we give this line, this tangent line, the right slope. So the derivative of that is cosine of theta. And if we evaluate that at 0, then we get that the slope should be 1. And we can also evaluate the function itself at 0. And now it's like we know the coordinate of a point on the line, we know the slope of the line, so we can give a formula for the linearization of f. So now we can say that f linearized would look like the slope here is 1 times theta minus 0, since that's the point where we're looking at, and then we would add to that the value of f of 0, which is 0. So here what we showed is that if we were to find the tangent line to the sine function at theta equals 0, that would look like just the equation theta. So maybe you're used to thinking about sine of x. In other words, if we had the function f of x was sine x, then its linearization would just be the function y equals x. So then what we could do with this is say, okay, well, if I'm considering equilibrium near theta equals 0, well, then the sine of theta is pretty much going to behave like theta itself. We can approximate the sine of theta with theta. And then this system becomes d theta dt is v, and dv dt is, I'm going to replace sine of theta with theta and write that first. And then we still have this 0.2v. And now this is a linear system, right? And we could find the matrix of coefficients for this. And then we can find eigenvalues for that matrix and then think about the stability of equilibrium in that way. Let me just say that the eigenvalues for this matrix, they don't work out great, but in order to understand the stability, we kind of just need to know the sign more or less. And so they actually wind up being complex. And you can verify that. But when we're working with complex eigenvalues, remember that it's going to be the sign of the real part that's going to determine the stability. And since this has a real part, which is negative, then we know that this is actually a stable equilibrium, and it's actually going to be a spiral sink, for example. but most importantly, this is stable. And that's what we kind of thought about, is that, okay, this analysis was only applying to situations when theta is small, or say close to zero. So if I'm considering the equilibrium, just the equilibrium when theta is close to zero, so when it starts off at its downward hanging position, makes sense that that would be a stable equilibrium. So this analysis really only applies when we're considering values of theta that are close to zero. So we're only considering values of theta that are really close in here. If we move to some other point of the line, well, this linearization approximating the sine of theta with theta is not going to be a good estimate at all. So if I want to study the stability of some of these other equilibrium, for example, there was an equilibrium at the point theta is equal to pi and velocity equals 0 when the pendulum was way up at its top point over here. This analysis isn't going to apply to that situation. So let's take a look at some of the other equilibrium on the next slide.